Uniform circular motion. Yeah, it is important that it's uniform, but it's also kind of inherent. We're going to add some other annotations to this, but for now, please just copy this down. Now, I'm going to do a little demonstration. We're going to talk about this conceptually for a little while. So once you've got that down, just give me all ears and eyes up front. Put this down. Well, let's get it finished, guys. Shouldn't take long. Chapter 3, starting chapter 3. No, I'm suggesting you get your notes done. All right, whether you're done or not, here I come. Let's discuss this. Uniform circular motion. Obviously, okay, guys, come on. We're talking about a very specific case of circular motion. It can't be elliptical. Question? It's the situation we're describing is uniform circular motion, very specifically a perfect circle in motion with kind of confusing, but a consistent magnitude of velocity. Theoretically speaking, we're going to be dealing with perfect circle. Our theory will be based upon that. And we discuss limitations. Science is never exact. Okay, this is a pencil spinning. I'm not going to spin the cart because the cart's quite heavy and could probably kill someone. This is a pencil spinning in uniform. Now again, not perfect, I know, but it's a good. Now, we are pretty familiar with dealing with forces and motion and how all of that works. If I give this cart a push, it will travel. It should continue to travel unless some other force is on it. Okay? Now, the case we're dealing with uniform circular motion involves a constant. So what do I mean by that? I mean the speed that this cart, and I'm going to cheat a little bit, so the spin of this car, the speed it is moving at any given time is going to be constant. We're not going to be dealing with accelerating much, okay? Now we're going to except it is accelerating. I want to explain why the car, even if the magnitude of its velocity at any given time is the same, that magnitude, why is it still considered? Yeah, we are going to have to ignore gravity here. Obviously, when I spin it like this, we are ignoring gravity in this case. We will actually conduct an experiment where we're spinning it like that to avoid gravity. Yeah. Right, it's changing direction, yeah? If my cart's moving so fast this way, and then I put a force on it, okay, so fast this way, and then I put a force on it that way, the velocity's magnitude might be accelerated because the direction of that velocity. I mean, we can do the exact same thing going forward backwards, right? The velocity might be the direction that's changed. Now, in uniform circular motion, we are under a constant acceleration, okay? And acceleration is a vector quantity. And the direction of that acceleration is not the same. It's constantly changing. Does anyone know what we can say about the direction an object is accelerating at any given point? Something that we can say, generally speaking, about the acceleration's direction at any point for that object. So let's imagine that scenario. So Max's proposal is that it could be tangential. I'll use purple for this. So there would be an acceleration that way in tangent to the circle. What would we predict that to do to the object's direction of travel? It's going this way. It's currently got a velocity vector of this. This actual direction of travel can be considered as a velocity vector with magnitude and direction, right? Velocity. Ignore air resistance. Ignore friction. In this case, we're dealing with a tension in that string of some sort. But what do you think would happen if we accelerated an object that was traveling that direction and we accelerated it that way? It would go that way faster, right? Is that what happens when I spin something in uniform circular motion? No, so the direction of acceleration is not going to be tangential. What other ideas do we have? Perpendicular, outwards, inwards, doing what? If it was going inwards, then the object would move inwards into the, like, spiral in and, right? If it was accelerating outwards, wouldn't it go that way? Wouldn't it go, woo? Yeah, it's attached to the string. What does that string do? Okay, let's talk about that string for a second. So here's the center. String is attached to the object from the center. And as we're spinning, the object obviously goes in this path, but we know from Newton's laws that the object shouldn't go in that path unless there's what acting on it? A force. There must be some force that is changing this object's direction of travel. Otherwise, it would just keep going outwards. And in fact, if I cut that string, that would just fly off, right? And you can do this like if you're in space and you're spinning something and you cut a string, all of a sudden it shoots off and just keeps traveling in that direction of travel, tangential. If our object happened to be over here and we cut that string, we would see our object travel tangentially that direction forever until some other force came along. But that doesn't happen because we've got our green string, which is applying what? What's our green string applying? Tension. What's tension? A force. A force due to tension. In which direction is that force happening? Perpendicular or towards the center? At any point, it's towards the center. Now, is that our net force? Are there any other forces acting on this? We're ignoring air resistance. We're ignoring gravity. Would there be any other force? Towards the center there or whatever? Yeah. Tension within the string and then tension of some normal force for whatever it's attached to. Let's ignore that. Tension does go both ways, so realistically the tension of the string would also pull that way on that central object, which would then have some normal force pulling against it. So in that case it's my hand, right? The string pulls the cart upwards, the string pulls my hand down, my hand pulls the string up, and we get uniform circular motion, right? In that case gravity is also pulling down, but if we ignored that. Okay, so ignoring what's happening in this center here, because they balance out perfectly, they become balanced forces. Is this our total force? Is this our net force? Anyone think of anything else that might be at play? Don't think too hard, there's not. Okay, so that's it. Which means what about our acceleration? Except there's only one. It's not two. We're not doing vector resultant vectors here. That's our force. That's our acceleration. Remember, F equals mass times acceleration. The acceleration is going to be the exact same direction of that force. There is no other force. That's it. Oh, yeah, the net force would be that force. Is that what you're saying? Yeah, absolutely. So we have an acceleration here. And it is where? What can we say generally about the acceleration? Constant, yeah. Assuming the tension force stays constant. Where does it direct itself? If I was up here, right, we're spinning around this way. My travel direction would be this way. But a moment later, my travel direction will be like that. How did my direction of travel change like that? How did my velocity change like that? I accelerated in this direction. How bizarre is that, right? But it makes perfect sense. Stop and think about that. If I'm traveling straight forward and I all of a sudden need to turn and go left, I need to accelerate to the left. So the tension applies a force towards the center. At every point, we are accelerating both tangentially, we are accelerating perpendicularly to the tangent at every point. And as a result, our velocity is in a continuous state of change. We are continuously directed to have a velocity that is tangential to that circle. Can you see that there from that diagram? Is that clear? Feel free to try and fiddle with the diagram yourself in a way that you are trying to develop this conceptual understanding. And call me over if you want me to check that you've labeled something with the correct notation and you want to know, is it right to say this? Can I draw this here? Can I say the force is that? Feel free to call me over and I can check your diagrams. But otherwise, this is really the summary of it, and we're going to make 2 notes about that. At any time, just put your hand up and call me over. I'll write those 2 notes for us now. Sorry about this. In the same direction. This is going to say. Sorry. Nailed it. Stupid big circle. I didn't even need the bottom half of it. All right, let me do a quick roam. pause for a moment. God, it is hot today. That's the magnitude. Yeah, you can talk about it. No diagram questions? No, that's cool. So for things that are spiraling in, yeah, the force inwards has to be high enough. This can have the force inwards that we don't get. You can do this, right? You can pull on the string harder. Eventually spiral inwards. So I just need a higher force of tension. The reason that doesn't happen by default is because we're reliant on a normal force. I'm having to keep my hands stationary here. I'm making that choice. If I was instead to do this, pull down like that, I would increase that force. I wouldn't make a choice that happened to match the exact. I'm choosing to match the exact. I could easily pull it harder and move it and change the direction and spiral. But I'm choosing to match it. Okay, are we good then? Pop quiz. Who knows what we call this? Action of accelerations and forces acting towards a center. Center. One of them, because there's two that you might think of automatically, one of them is a lie. The other one is physics. Hands up if you've heard of centrifugal. Hands up if you've heard of centripetal.
They're the same thing.
Hands up if you prefer centrifugal. Hands up if you prefer centripetal. So, you may have heard of centrifuges. If you've seen those rides where you get stuck to the walls, or you've heard of blood being separated into plasma and cells or whatever, by being spun really fast, the denser thing gets flung to the edges. Or if you've ever watched your washing machine flick water from the middle of the object out to the edges and go through little holes, those are centrifuges. They're called centrifuges named after a centrifugal force, which is believed to project things outwards from a spinning circle. It's a lie. It's Newton's first law. Objects in motion stay in motion. If you spin upwards a piece of clothes and it's got water in it, and then all of a sudden accelerate it that way so it changes direction, the water wants to keep going that way. So at the top of this, the water will just keep going that way unless you apply that same force to water. Now, water being water can just fall out of the clothes and fall through the holes. Clothes being clothes get accelerated inwards by a force pressing against them from the drum of your washing machine. So the clothes keep accelerating towards the center and spinning in a circle. The water gets flung out to the edge and drains away to your pipes. Make sense? Kind of cool? Centrifugal forces are lie. Centripetal is what we're talking about here, and that's what our title is going to be. We're going to have centripetal acceleration and force. Centripetal force, centripetal acceleration. Let's break them up into two columns. Yes? Yeah, pretty much, yep. Yeah, it's all basically a lie. But I mean, they're more useful lies. I'll be honest, I don't actually know how this is spelled, so I'm hoping I'm right. You know I'm terrible at spelling. Do we need definitions for these, or? I feel like we don't even need definitions for these, right? This just is this. F, C. And there it is. That's how simple it is. Now remember, we are not dealing with things that are accelerating in the sense that their velocity magnitude is changing. We are looking at situations where we have uniform circular motion, therefore a constant magnitude of velocity in this circle. Okay? So these V's in here are going to be the tangential velocity at any given point, which will be the same at any given point. Little box, oh, it's just an object and a right angle. Just helping you appreciate that this is a right perpendicular sort of situation, but it's also representing an object. Yes, so these are taken straight from your formula books, except for some reason, little notation here, for some reason, the Queensland Syllabus formula book calls this FNet in formula book. I don't know why. I guess because they're making the point that when we talk about uniform circular motion, the centripetal force is all the forces. It's the net force. You could theoretically be given a question where there was some other force at play. I can't imagine what that would look like, but it shouldn't be too much of a challenge if it were to come up. You would just do your net force calculations, and yeah, not much changes really. Okay, you'll probably notice that these, for one, the velocities are squared, which is somewhat interesting. And for two, they involve the radius, okay? Basically, the derivations for these come from the geometry of circles. So the circumference of a circle is 2 pi r, the area of a circle is pi r squared. We start to see these sorts of relationships in the formulas for the physics of uniform circular motion as well. I don't actually know how to do the derivation of them, but it comes from just that simple F equals ma stuff. And you just substitute in the idea that we're changing direction in a circle. So I'm sure you can find some pretty good videos online if you wanted to know about that, but it's really beside the point. Now, the last thing I want to talk about is, well, I guess there's two things really. Velocity and period. We have one other formula, which is velocity. Oops, take me back to black. Velocity equals 2 pi r over t, okay? Now for these, obviously, m equals mass of object. I don't know whether you need to make these notes. Hopefully you're pretty familiar with some of this notation by now. V equals velocity, and it's technically that tangential velocity. And it's also technically instantaneous at any point specifically. And then obviously r equals radius. Hopefully that's apparent. If it's not, sorry, I don't mean to put you down. But you're probably fairly familiar with some of that. Now, what you might not be familiar with is down here, where t equals period. Now this one, I do actually know the derivation for. If you look at this and you think back to what velocity is change in displacement over change in time, right? How far did we go? How long did it take? Well, how far we went is we went in a circle. Anyone know the formula for the circumference of a circle? 2 pi r, right? So how far did we go? We went one full circle. How long did it take? It took the period. What do you guess the period is? The time it takes for one full circle. It's how much time has passed. So period, I might go to the next page, but if you guys want to squeeze it in here, feel free. But I'll go to the next page and just write a definition for period. Is everyone okay if I skip ahead? Anyone need 5 more seconds? Kobe? Go. You need me to go back? Okay. So period is the time for one full measured in seconds, of course. SI units for time. Is that fine? That makes sense? How long does it take to do a circle? How big is the circle? That gives you the velocity. I think we're probably ready to start jumping into some examples. All right, let's do a little check for understanding. In your books. Okay. Check for understanding. Arrogant to assume. Therefore, for someone who it's a metaphor for not understanding physics of wax and heat.
But shouldn't it? Wait a minute, it's not accurate?
Terrible movie.
You don't know how close it was.
Oh, this should not take long. To be fair, this doesn't explicitly say which way we're going. Assume that we're going from A to B. I guess I believe that everyone. I've dealt with. Have you ever heard of that philosophical question of what do you think about a man who what's worse there if they let their life or if they probably let them. So if you kill a murderer, are you good? he killed them. How is that not relevant? That's exactly the point. My point is that people are inherently good, and you never know the situation. So it would be arrogant to assume that you can make the choice on who can die.
Okay, in any case, not
It's good chat. Let's continue into a break time. Okay. I guess I don't necessarily believe that they're good at heart, but I believe that there are motives for their actions. Yeah. Right. It's not good, it's just with reason. Identify the direction of its velocity vector at points A and B. Velocity at point A. Velocity at point B. Again, assuming we're going from A to B. If we were going from B to A, then it would be the opposite. Or if we were going from A to B but clockwise, then it would be different as well. Identify the direction of the force vectors at A and B. Bam. That's perfectly central. Don't argue. If that's not what you put on your page, you have some serious misunderstanding and you need to ask me about it. Okay? No, if you said left, right, up, down, whatever, yep, fine. Totally fine. We just drew arrows or whatever. Okay? If you got that wrong, call me over. We'll do it together. All right, let's do some examples of average velocity, centripetal force, that sort of stuff. On 3.2a. Worked example 3.2a. What's the period? Give me the number. Not a trick question. Girls, finish up your conversations. Max, Alex, finish up your conversation. So in this case, they tell us the time for one revolution is 3.1 seconds. What do they mean? They mean period. T equals 3.1 second, which equals the period. They also tell us the length of the string is 2.2 meters. What is that? What is that in terms of something that's relevant and important to us? Radius. Radius equals our radius, right? So interpreting these in terms of the variables we're actually looking for is a worthwhile skill. If they had have said the time for 2 revolutions is 3.1 seconds, what would you have to do? If they had have said the time for 2 revolutions is 3.1 seconds, what would you have to do? Divide it by 2, halve it. You want the time for 1 revolution. If that was the time for 2 revolutions, you need half of that time. Yeah? If they had said the time for a quarter of a revolution, no, I'll stop there. You get the point, right? Okay, let's do this example. Part B is the average speed. So B, notice they say average speed. That's going to come up a lot. They also say speed, not velocity. So we're talking about that magnitude. We don't need to state a direction. So average speed of the ball, this is just going to be our V formula, which was VC. Did we end up using that notation? What new notation did I use? Back here. Doesn't really matter, but VC. The reason we don't say VC is because it's not really centripetal velocity. Okay, doesn't happen towards the center, so we'll leave it off. Just V equals, what was it? 2 pi r over t. 2 times pi times 2.2 divided by 3.1. Oh, this is an easy one. That basically cancels out to 1. This is 2 by 2.2. That's 4.2. About 4.2? Was basically what I said. 4.46 watts. No, meters per second, yeah? And note that we are using meters per second, so we needed to make sure this was meters and this was seconds. SI units are really valuable here, critical here as well, okay? Average speed of the ball. C, velocity of the ball. What's that really asking us? What's the difference between this, which is the speed of the ball, and this, which is the velocity? Right, they're the same except for the direction. How are you going to state the direction of the velocity of the ball? They don't give you a specific point, do they? She's just whirling it around. How are we going to state that direction? What's a general way to state the direction that is always true? Forwards relative to what? Forwards mean? Not going straight, it's going in a circle. Let's go back to this diagram. We want to talk about the velocity, generally speaking. What can we say about its direction? It's not horizontal here, that's vertical. Oh my God, stop. What's the word? What's the word to describe this? Perpendicular to what? Sure. There's two ways you can say this. Parallel to the tangent, or just tangent at a tangent. You can just say it's tangential, tangent, or perpendicular to the string, or whatever, perpendicular to an imaginary line to the center of the circle. Okay, that works to describe that velocity's direction at all points. Not perfect though, because it doesn't tell you whether it's going that way or that way. Both of them can be tangential. You know what I mean? Anyway, doesn't matter, but that's fine. Let's do another example and then we're done. One more example. Anyone need 10 more seconds? Go. Kobe, turn it off, put it in your bag. All right, here we go. Velocity is just speed with direction. Velocity is a vector component, speed is a magnitude. It's a scalar. Have a read, write down any important information and translate it correctly into what is relevant for us. Kobe, have a read, write down any relevant information and translate it into what is important to us. Ten seconds before I do it, Max. Have a read, write down any relevant information. All right, here I go. I know that diameter equals 630 millimeters. That's not useful to me. I want radius. Radius equals 0.315 meters. I know that rotation is 850 rotations per minute. So rotations, RPMs, equals 850 rotations per 1 minute. That's not useful to me. How many rotations do I want to know about? One. I want to know one rotation. I want to know how long one rotation is. If I'm given a rotational speed like this, I need to convert that into a period. I want to know what this is per how many seconds if it's one rotation. All right, let me show you an easy way to do this. So we're going to replace that 1 minute first with seconds, so we're dealing in SI units. So 850 I'll just say rotes per 60 seconds. Now at least we have the units we're interested in. And then how do I get this to be a 1 without totally breaking my ratio here? Divide by? Top and bottom divided by 850. Divide by 850. What I do to the top, I do to the bottom, divide by 850. That will give me one rotation per how many seconds? You got it? Did you do 850 divided by 850 to get 1 and 60 divided by 850? Or did you do 850 divided by 60? It can't give you the same answer. $60 is being divided by 850. It's 60 divided by 850. What equal the same? This is all I need you guys to do. 60 divided by 850. Right? 850 divided by 850 is obviously going to be 1. 60 divided by 850 is going to be 0.07. Let's leave it there, 0.07. So what's our period? Remember what it is conceptually first. 0.07. The time it takes for one rotation, t, equals 0.07 seconds. Rotations per minute is not useful, but it's very common. So get good at that. Okay? Does anyone want me to go through any part of that little unit conversion again? No? I can do it differently, do it another way. All right, well, let's finish the question. What are we actually looking for? Average speed, yeah? What's my formula? V equals 2 pi r over t. 2 times pi times 0.315 divided by 0.07 equals 28.27. 28.27 meters per second. No questions about that? Anyone want me to go through any part of that again? Nope. You guys are on the ball today. Is this kind of easier? Yeah? This is all right? Okay, cool. All right, well, I'll give you 2 questions. We should be able to wrap that up before lunch. That shouldn't be a problem. I'll chuck them up now. Sorry, did everyone have that? Was everyone fine? You want me to go back? Give me a second. Hang on, I'll get this stuck in. Not going to be too much longer? Good now? All right, here's your exercise. These are a couple of questions from Check Your Learning 3.1, 3.2. Alrighty, guys, get this done before lunch. Thank you.